Okay, it's noon time. I'll get started. Today we don't have any student log into this session, so I'll actually just go over some of the things that I would like to cover. Just go over the basic theory of the remaining of the chapters. First, we are on chapter 12 today, 12, 13, 14 today. For our course, we have chapter 1, 2, that's actually on basic robotics. Chapter 3, 4, 5, 6, 7, 8, 9, that's actually on kinematics. So if you look at the subname for the class, we have the K, that's a kinematic. And then we have 2 chapters on sensor. And then from chapter 12 and beyond, we are on the control and control architecture. These are unit 4 for our course. Hi, good morning. Okay, so anyway, today we actually starting the chapter 4, the unit 4 for our class. So it's a robot control architecture, and we will go over the basic architectures. First, let me explain one more time about the mathematical modeling, the importance of mathematical modeling. Why modeling is so important and it's core for our basically our robotic course. So modeling, actually, we do teach you the modeling for the actuator. I'm sorry, this is too thick. Let me try a thinner one. The new pen is actually different width. So we talk about modeling. And basically, mathematical modeling is very important for all of the DSP project or communication chip project or any of the project in EE. And the reason has been like, okay, if you actually look at our system, we do have the modeling for the manipulator. That's on robot arm. So if you have a robot arm that actually is, well, we modeling on. Second, we do have mathematical modeling that you need to use. For example, on the sensor would be here or here, actually taking over the modeling for the environment. Third modeling is that if you have a robot and you are moving with wheels or tractors, then you need to provide a modeling to actually see where your robot is moving. So there are manipulator that you need to model. There are sensor you want to model. There is also the mobile wheels that you need to model. So basically you have 3 major modeling, and then your whole system will be controlled by a GPU or by a CPU, by some sort of controller to control everything, coordinate everything, including the input from sensor, the movement by your tractor, and also the manipulator for your robot arm. So basically, this is quite important. Okay, this is actually quite important to build a mathematical modeling. Say, hi Monica, how are you? Hi Monica, how are you?
Hi, Professor. I'm good. How are you?
No problem. I already get started. So today we are talking about the controller architecture. So we talk about the manipulator sensor part, and today we are talking about the controller. And right now I'm talking about the importance of mathematical modeling. Okay, so I get started already. But anyway,
Yep.
so we cover this different modeling, but in fact, this mathematical modeling can be used for many applications. So when you design DSP, digital signal processor, or you design a communication system, okay, you need to actually work on the modeling for the system first. So basically, let's use a communication as an example. Originally, your data is 0110, something like digital. And then you need to convert it to some sort of signaling. So this signaling basically is what is actually would be like in hard disk, you may use a PRM for partial response modeling, a multi-level signaling. So your signal become multi-level signal. Okay. And then you actually convert it to voltage and currents by transformer. And then receiver have another transformer, and then convert it back to multi-level PRML, partial response module circuit, and then you convert it back to digital world. So you need to model your system from the transceiver to receiver. And this, we call it a closed loop feedback modeling. So before you actually design your hard disk channel or your Ethernet, you have to build up such a channel first. You work on cell phone communication channel is the same thing. You need to spend time to work on the mathematical model, and this is actually done by MATLAB or PyLab or C++. Okay, this is actually for the modeling of the system. And then from this level, you actually go to the next level. The next level, you will actually work on the register transfer level modeling. So you actually use a Verilog to design your register, your adder, ALU, okay, your write-back system, whatever. This actually we call it data bus. And your controller, the control unit, that control everything here. Okay, so from your signal modeling, that's mathematical modeling, you model it to Verilog. This is second level in your design, in your system design. So from Verilog level, next level is gate level. So usually you use a Synopsys synthesizer to do logic synthesis, and then you become having design in gate level, okay, something like that, adders, whatever. So that's gate level design. And beyond this gate level design, lower than that, you become doing the so-called placement and routing. So you actually convert it to some sort of layout at a transistor level. Okay, at the transistor, because you use the cell layout, and you become the transistor, you become having the gate level. So this one is gate level. Below the gate level, actually it becomes the transistor level. I'm sorry, not gate level, transistor level. And then you'd have to do spice simulation right here, okay? H-spice or spice simulation or some timing rule simulation in this transistor level, okay? And then beyond that, you go even lower, you become building the transistor. So you need to prepare the photo mask Okay, whatever. So what I want to say is that engineering, actually, we have a lot of level in terms of the design and layout and the final verification for IC chip. But anyway, the mathematical model is providing you the architecture and also top level, system level view of the overall system. So we do have many loops that we need to look at. Okay, so this chapter 12 is on the overall control architecture. Okay, so there are different, you need to know about different kind of control architecture and the different level of the design. Okay, different level of the design. So the architecture is the overall overall system view of your robot. So there may be some sort of the sensor feedback part. There may be wheel controller. There may be some sort of velocity controller. That's a feedback loop. That's an overall system that actually. So basically, the control architecture in charge of your manual input may be, your sensor input may be, the movement of the robot as well. Okay, this everything related to robot will be modeled into your computing system. That your system block will be handling everything. Okay, that's actually why we have this control architecture. Then there are 4 different kind of control: hierarchical, reactive, behavioral based, and hybrid system. Okay, so hybrid is missing everyone. So we don't need to talk about hybrid. Hybrid actually missing everyone. So let's look at the 3 major different type, that actually hierarchical, reactive, and behavioral based. Okay. So first kind is called, these are 4 kind of the control: deliberative, reactive, hybrid, and behavioral based. So deliberative, this deliberative control means that it's also called hierarchical. So hierarchical is, in other terms, actually deliberative. So this one say that you actually will think hard and act later because your loop have sense, plan, and act. So if you think hard in planning, then it's called hierarchical, or it's called basically called deliberative. Okay. So we say that our minimum requirement for your term project is that you must have a sense, plan, and act. Okay, let's just give you some sort of input and take reaction on the input. And in the middle, you need to do control. So that's the minimum architecture that required for a robot. Okay, it's called hierarchical or deliberative control. Okay, and then if you are reactive, means that you don't have planning. You sense, you react. Okay, so these 2 systems actually are what? If you actually are familiar with the Israel and the Middle East conflict, okay, so Israel have some sort of Iron Dome. Okay, we actually, I'm not either taking any side. Okay, I actually have no political interest. But basically, they have the so-called Iron Dome. Okay, so here you have a radar, and it actually sends any missile coming in. Okay, so let's assume there is a rocket shooting here. Okay, multiple rocket actually trying to invade the territory that this Iron Dome covered. So this actually, your radar need to detect it. Your radar will detect it. So this part we call it sense, right? And then there are 4 missiles coming to attack this whole unit at the same time. So which one you actually we shoot it down first? That you need some sort of planning, right? And then eventually you actually order some sort of the missile right here. Okay, you have the missile right here, and you shoot Samuro-Taki. That's called sense, planning, and action. Okay, action. So that's using this Iron Dome, you will see that, okay, these are the modern defense system. Modern defense system is also a hierarchical system. Okay, you do have the so-called sense, plan, and act. Okay, and reactive actually is simpler usually. That means you may have a radar, okay, and a missile coming to attack. You sense it, you shoot right away. Okay, you don't wait for the computer to find the best target or prioritize the importance of the target. You will shoot it. Usually like some sort of fast gun, okay? Fast guns like that. So that's called cross-in combat system. So the cross-in combat system in Navy, in US Navy, we call it cross-in. I'm sorry. My keyboard is not reacting. Sorry. Okay, I happen to serve in the Navy for multiple years. So, okay, it's called crossing combat system. So crossing combat system usually do not have the planner. Okay, it actually just see that there's already some sort of target moving into your range within only 2 miles away. Okay, so you don't have time to really do deep calculation. You have your radar on top, you have to fire right away. Okay, this kind of a system is automatic, but actually it's called reactive. Okay, it's called reactive. So these two kind of the system actually is based on some sort of feedback loop. And then 2 plus the behavioral based means that you have plans, you are trying to be actually complaining as hard as the hierarchical, but you don't want to waste your time. So basically you have plan A, plan B, different kind of result. You actually doing the parallel processing at the same time. So based on the census result or behavioral result, you decide that whether you use the plan A or plan B to save time. Because this hierarchical problem, system problems that if you actually overloaded, you actually do saturated attack, your computer may not be planning it quick enough. Okay, so your system may be bombed before you actually take action. So that's not good. You actually trying to actually put multiple plans together in order to basically improve your behavior. Okay, based on your behavior, and you decided which plan A, plan B, or plan C you will use. Okay, so basically, let's assume that the missile detection system, plan A is counter attack on Russell, okay, on rockets, and rocket has no control. It will not change its trajectory. Okay, in those kind of low level attack, you do not need to use a high valued missile to attack it. Okay, to counter attack it. If you sense that your missile is actually off, it can change trajectory by itself, then you have to use a very expensive counter-attack weapon. Okay, so this different planning, actually the system will decide which one you attack. Okay, and then the third one is actually called hybrid one. Hybrid one means that you have a planning system, but it is optional. You can use a sense and action, and sometimes use a sense act, plan act system. Okay, So also depend on the target you will make different. So these are four type. Basically you need to know about these, and these. And then the fourth one actually is a combine of everything. And we say smart control is that if your planner involve AI, then it's smart control. Okay. So if your planner is not AI, it's just normal processor, it's still a robot, but it's not smart robot. Okay. So smart robot or not smart robot, basically looking at whether your robot has a smart planning or not, AI based planning or not. So far, any question? So far, any question? No? Okay, so today we actually explain this four different kind of control, okay? And then the bottleneck is always at the planning. That's why we have so much trouble. And if you do AI, that the planning will take even longer, okay? But AI will give you much better planning compared to the traditional planning, okay? So we do smart planning, but it will pay. We have to pay price. If you don't have a planning part, we call it reactive model. Okay, and this reactive just sense and there is no planning. So that actually is a faster response, but may not deliver the best response. Okay. So here we have comparison for the two different kind of the robot models. And then another kind called behavioral-based architecture is actually combining multiple plan. Okay, so your robot usually may sense and react, but behavioral-based means that, okay, you may have a few scenarios you actually already know. That would be a robot to push the door or go through the door, approaching an object or follow a wall. This four plan is what basically your robot may take. Okay, so you actually, when you do computing, you do go through the four different paths at the same time. And then your arbitrator decided whether you decided to push the door or go through the door or approach the object or following the wall. Okay, your controller would make decision which one you will pick. Okay, this is called behavioral based. So that means that you actually already pre-do several different planning at the same time, so that you just pick A, B, C, D, one of the plan. Okay, instead of you sense and then calculating, that actually, and then choose A, B, C, D different plan, that would take a long time because your plan will take a long time. You actually consider that you have a different signal input. You sense, you already calculate four different plan to do action, but later you will pick one of them. Okay, you will pick one of them. It's called behavioral based. And you have behavioral based, let's assume that you have a vacuum cleaner. Okay, your iRobot. You go. Most of the time you're going, so you actually just approach an object. Until you actually see there's a wall, then you change it for the picking a wall. But no matter whether you are approaching an object or following a wall, basically you actually update your computation for every option at the same time. Okay, at the same time. And then your arbitrator, your controller will pick one of them to do it. Okay, this is so-called behavioral-based architecture. Okay, and then we go into the choice of the robot architecture. We have four different kind of robot architecture, and then here talk about different in terms of implementation cost, in terms of the control effectiveness, in terms of the system type. You make a choice on the robot, okay? And the next one is that you have to think about hardware implementation. Do you want to use a the traditional low-cost adaptive filter design or ASIC design or DSP microprocessor design or deep learning neural network. Okay, nowadays everybody say, oh, you have to design a robot, but usually robot cost is very high. Okay, smart robot cost very high. You may just need ASIC or DSP or even adaptive filter. Okay. So that is something you want to study, whether you have enough control versus the cost you are willing to pay. Okay, that's choose a system or you that fit your project. Okay. Okay, so that actually. So when you design, you also need to choose a robot OS. Okay, this robot OS, ROS, is one of the commercial system for the robot. So when you build a robot, you also would choose a operation system. So this one is called robot. Operation system. Okay, so ROS is widely used for robot. It's called robot operation system. Okay, so you choose an architecture, and then you also need to choose. You also need to choose a operation system. So, and then there are tons of material that you need to go through. Okay, for the choose of the operation system. So you have to consider response time, environmental model, internal state. Okay, a lot of issue over here. Okay. Okay. Anyway, this one is the choose of architecture, implementation, hardware type, and also operation system. And then you do system modeling. Okay, and then to make sure that you can predict the performance of the system. Okay. Okay. So far, any question? No. Okay. This one we go into smart robot control. Okay. So basically, smart robot control, as I said, you have sense, action, planning, and action. The planning part can be traditional computer, then we cannot call it smart robot. Okay. So basically, if your planning part involve AI, involve reinforcement learning, involve deep learning, then we call it smart robot. Okay, then we call it smart robot. So basically, a robot can be traditional robot without deep learning robot training. Okay, so robot is just a humankind arm or humankind body. Okay, humankind eye, computer vision, but it may not be smart robot. Okay, so we actually classify a robot as a smart robot, basically based on its planning stage. Okay, so you have sense, plan, and action. Your planning action, if it involves neural network, then we say it's deep learning robot. Okay, so it's a smart robot if we say that. Okay, so case number one, let's look at one design for the system architecture. So number one, we want to develop a temperature control. So before you develop a temperature control, you will build up the system model. So the system model is that you do have output temperature, the temperature right here. You use a sensor to sense the temperature. Compare with your set point. For example, your set point maybe in the summer, you set it to be 69. Okay. In the winter, you set it to be 75, whatever. Okay, so your environment sensors a result will compare with your set point. Here it says your summing junction. It actually summing means plus or minus. Okay, and you actually would see the error. So if you right now it's actually 64, your goal is 75, then you need to pick up. Okay. If right now your temperature is 90, your goal is 69, then you need to drop. So this is how the feedback loop will work. Okay, so before you build a robot or whatever temperature or actually automatic control on your AC, you build up such a loop, okay? And the second one is automotive speed control. There are several kind of parameter you need to model, okay? So first, after you have the system model, then you need to do process schematic. Draw down this process, and then there are a lot of measurement or parameter you need to take care, okay? List down the parameters. And then you actually design the block diagram. You end up with this one. Actually, the block diagram is done by MATLAB. Okay, MATLAB. If you look at it, it's actually a MATLAB signal processing package. Okay, and you model everything. Okay, you model everything for that for a system, and then you do simulation to see if the system performance is what you want to have. Okay, and after that you actually look at the implementation part. We call it design. Okay, and the design part, you actually will go through the choice of general purpose processor like CPU or an ASIC processor, okay, or an ASIC application specific processor, or application specific IC design. Okay, so basically these are different kind of design approach. Okay, so number one and number two involve processor. Okay, you have instruction set and actually processor. Number three, no instruction set. Okay, it actually based on it's actually hardwired chip. Okay. Okay. Anyway, these three types you all can use to design your control system. Okay. Then you go into your DSP or controller design. So this part we call it hardware software co-design. Okay. And you design it based on your design. You can actually design your chip. You can also design the software. Okay, there's different automatic levels, whatever. You can also use a finite state machine to handle it. Okay, and you can do SCP. But here, actually, this project is have to do it before you know the detail. Okay, but I just go over the basic concept of hardware software co-design. And this part is the so-called X major, okay, electrical engineering and computer science, okay, X major. At MIT and Berkeley both have X major. Okay, anyway, these are the chapter 12, okay, the control part, control architecture. Then we talk about from system modeling down to design. Okay, so that's actually the overall design of flow for the controller. Then we have appendix in the textbook called feedback modeling. It's called dynamic modeling. Okay, this chapter give you the detailed system simulation modeling. Okay. So if you do modeling for neural network, it's very similar to this one, dynamic system. Okay, very similar to this dynamic. So let's see. Let's actually search for internet. And here we do have a, let's see. Check out the ASU. Okay. There's some video in the internet that you can search for that actually is working on the very good working on the dynamic system. Okay. So dynamic system, this field, I'm sorry. Dynamic system actually, let's see this one. MATLAB has the dynamic system simulation, okay, to do modeling. And then there's a professor in, I believe it's ASU, he has a whole course on dynamic system simulation. I cannot find it right now. Okay. Okay, anyway, this dynamic system simulation itself is a long story. So basically, you set up your dynamic model. Okay, what is dynamic model? It's actually using the differential equation to model it. That's actually called dynamic model. Okay, why differential equation? Because if you have a tank, right, you instill water, you leak water. Okay, so you balance your water level. If it is a parameter, it depends on your input, inflow, and your outflow, right? And this actually your input would be a dV dt. Okay, it actually is this V is volume. Okay, so you have your flow speed. Same thing, output is your flow speed, and the whole net balance of your water level would be a differential equation. Okay, so here we have the charge conservation, means the total charge is the same. Total mass the same, we call it mass conservation. Momentum conservation, we have concentration conservation or current, some sort of balance in your dynamic system. And you use a first order or second order differential equation to model it. Okay, if you involve multi-directional, then it actually you do see the multi-directional derivative operator. Okay. Anyway, you actually build in your dynamic system modeling. Okay, so usually it's a differential equation or partial differential equation. So first example is you use the water tank. They are inflow and outflow. Okay, and your dm over dt, your mass change will be the input change of the mass minus the output change of the mass. That means that how fast you actually inflow, how much is the inflow of your water and how much is your outflow of your water. Okay. Based on the two, we set up a dynamic actually differential equation. Then you kind of can use the Euler method to solve it. Okay. And you can transform it to using the Laplace transform to make it into the frequency domain. Okay. And then we do have the Python simulator. This one can be downloaded from our system, okay, to tell you what is the integral result. Okay, anyway, that actually is the first simple dynamic system. You do have one variable to control and two variables to control it, okay. And then you can solve with the ODENT, okay, it's actually original differential equation integrator. Okay, ODEINT is actually ordinary differential equation integrator. Okay, you use that to solve it. And this ordinary one is actually in the SciPy's integrator. Okay. You can get this ODEINT function. And there's another package called Gecko. Gecko, you can install, okay? It's for free, okay? Gecko is also for differential equation. Okay, anyway. you can model this one for the simple differential equation, okay? And you do the result like that, okay? Okay, so we go to several different simulation. Okay, here another integration, okay? So basically you have to be able to model your system model into a differential equation before you can solve it, okay? And to solve it means that we want to find the time domain result. Differential equation basically tell you where your system variable will go. You usually like similar to vectors, but your result over the time is what we really concern. Will be the integration of it, okay? Okay, and then you have the so-called balance of equation. Balance equation, and you solve the equation. Okay, whatever. Use the balance to set up the equation, okay? And then you do simulation, okay? And then you can linearize your differential equation. Whatever is actually is a technique. And you have to derive it. Okay, there are tons of story behind it. We do give you some sort of maybe, and then you can solve the equation and then do practice, okay? We cannot go into the detail because this actually take a long time to finish, okay? Just go give you the idea of what this chapter is all about. Okay, and then there's a dead time analysis. A lot of math, and then you have to study the Laplace transform. So Laplace transform, usually when you study in electrical engineering or mechanical engineering, usually there's a system and signal course. You will definitely pick up this Laplace transform or Fourier transform, okay? Right here, we don't go over it too much, okay? You have to know about the Laplace transform to make your differential equation much easier to solve, okay? So Laplace transform. And then process time delay. Okay, and then you from Laplace transform you have to can set up the so-called transfer function. Okay, transfer function basically teach people what the system is, and usually is represented in Laplace transform S domain. Okay, S domain parameters. So you will have a box that joined by a lot of S equations. That's called transfer function. Okay. To here, we don't have much time to go over to teach you everything, but you have to do self-study, okay? About what is this Laplace transform system functions. So we do have some simulation as well, okay? We do some simulation on this Laplace transform as well. And you need to install a Gecko package. Okay, whatever. And then you can use the Laplace system to analyze the system stability, okay? The system stability usually is concerned with the, when you go shoot up, whether you do stable converge, or you shoot up actually end up with a growing divergent system. Divergent system we say is unstable. Convergent system we say is stable. Okay, and how fast you can stay converge you can converge. It's also a concern, okay, and it all related to your system design. So whether your system diverge or converge actually is the main issue that we talk about, okay? And here teach you how system will diverge or converge, okay? So you will do stability study, okay? Okay, anyway, this is chapter 13, okay? So basically chapter 13 will go into a control loop to set up the dynamic system and then study the time domain result, frequency domain result, and then study the so-called transfer function and the stability of the system, whether it converge or it diverge. Okay, that's the main topic that is chapter 13 do. But usually if you go to EE or you go to mechanical engineering, they will have a course called system and signaling, okay, or system and signal. They will teach you this kind of dynamic system simulation, okay. Any questions so far? Hello, any questions so far? In a way, I have to say that, you see, everything that we pick up is a big course, okay? Even this dynamic feedback loop simulation, it by itself is a course, okay? And the purpose of this course that we are teaching, 65K, this robot course, is actually assuming you that you already know about some coding, maybe Python, okay? Also, this system and signal course. You also need to know about computer architecture. You also need to know about differential equation. So basically, all these combined, we have this robot course. And also, we only have 8 weeks, okay, compared with other people's 2 semester, 16-week course. For example, in Berkeley, we are really short. So we cannot actually go into every detail of every subject. Our purpose is provide you the introduction, help you to get some sense of what they are, okay? That's what we can do right now, okay? We actually do introduction and give you some sense. Okay, give you some sort of sense about what robotics is all about, okay? And if you are really interested, you have to take many courses, make sure that you really understand the topic, okay? You have to take more course and also involve more project, okay? To know in more detail. Okay, next one, we'll go to the brief review of the chapter 14, control loop. So we have system modeling. We know about computer architecture. Next one, we are moving into the so-called control loop design, okay? Given the model, given the control approach, we will look at high-level modeling, control loop, and low-level modeling, okay? Well, what is the difference between high-level control and low-level control? High-level control is the so-called model, plan, act approach. Usually, this one is handling the whole loop, okay? By the word whole loop means that high-level controlling is this whole loop. It's called high-level controlling. Low-level controller is that specific on the controller, your system variable versus the output. That is a low-level control, PID control, proportional integrator differential controller, okay, for your motor speed. So low-level control means only the control loop, only the one that control your system variable. High-level controller means that your overall robot architecture. Okay, these two things are different. Okay, these two things. So first thing, let's look at the low-level controller. Low-level controller. Okay, I'm not talking about high-level controller. Low-level controller, you have proportional interpreter and differential controller. Okay, and then these three different controller will have different response. So this is a proportional integrator controller, proportional controller, proportional inter. So when your system gets stable, how fast you get stable? Or is there some sort of offset that you experience? Okay, these are what we're concerned about at the low level controller. And the new architecture had a proportional, this one summing point. Okay, so your desired temperature and your current temperature, do comparison and decide what control variable, say some sort of C or D, you will control your temperature. Okay, in right here, you have three type of controller. And this different type of controller will have different system response. Okay, so we do simulation on that controller design. Okay, for different modeling, PID modeling. Okay, I give you the controller of different type. Okay, different type has different response time. Okay. Okay, anyway, any questions so far? Any questions so far? No? Okay, anyway, those are low-level control loop. Okay, so you have open loop, proportional controller, proportional derivative, conversion integrator, derivative control. And then those loops can be used to control your velocity, your motor. Okay, and then you actually set up the simulation for how fast you can control your motor. The systematic offset, if they are, how to improve it. Okay. Okay, so we do have different kind of PID structure to help you optimize it. Next one, keep it in a straight line. Your car with motor, but your two wheel may spin at different speed. So using that, you can control your direction, right or left. Okay. So here we do have also have the direction controls. Okay. Okay, next one is proportional only control. We talk about the proportional only, the control loop part. Yeah, tons of parameter. Again, you can set up this controller and do simulation to figure out whether your system will perform well or not. Okay, this is the part that computer science can help. Okay, and the offset and possible system issues. Okay, we do have some simulation there. Then a lot of math following. Okay. So this chapter is to go into the low level controlling design. Okay. And then the next week, last week will be on the high level control. Okay. Any questions so far? Hello? Any questions so far? Okay. No question. I will be up to here today. Okay. If you have any question, let me know. So far, I think that some student already off track, already not able to follow. Okay, it's okay. I will still grade your homework, but you need to pick up. Okay, you need to pick up. Our purpose is not to scare you, but to encourage you to study. Okay, so try your best. Okay. Okay. See you next time. Bye bye.